So today we're going to talk about traveling waves. Now in the past you've probably seen repeating waves, which have a sinusoidal shape to them, a repeating pattern in space. But we're going to look at some waves that have a very non-repeating pattern, such as a pulse that's going through space. So as an example, let's talk about the Gaussian function. The Gaussian function has the following form. It's an exponential, but with the exponent completely squared. So the exponent is always negative, with the minus sign out front of the squares. The x minus vt tells you that it's a traveling wave, since all traveling waves are a function of the quantity x minus or plus vt. So what we want to determine is which way does this wave travel. Now you've seen before that for sine waves, if you have x minus vt, then the wave is traveling in the positive x direction, whereas if it's x plus vt, it's traveling in the negative x direction. But is that true for non-repeating waves as well? We'll explore that right now. So how do we tell which way the wave is traveling? First, let's construct a plot of the function as a function of x with t equals 0. That way we get rid of the time dependence for now and look at the initial wave. What's good about this is that the shape of the wave doesn't change with respect to time. So the shape will be the same, but where it is on the x-axis will change. So let's make a table of values of x as multiples of w, that parameter in the denominator of the exponent. The w tells you what the width of the pulse is, and we will see that more or less. So let's make a table of x equals 0, w, 2w, 3w. And since the x gets squared eventually, we know that this is an even function, so negative w will have the same value as plus w. So let's determine the values of y for each of these x values. So the exponent, when x equals 0, will equal 0, since 0 squared divided by anything is still 0. So the exponent part will equal 1, which means y is just the amplitude a. For x equals w, we get w squared over 2w squared. And e to the minus 1/2 is 1 over e to the 1/2, which is 1 over the square root of e. And that's about 0.6. So I'm just going to write 0.6a into that part. For the 2w, x equals 2w, we get 4w squared over 2w squared. That's 2w squared. And that value is e to the minus 2. So e to the minus 2 is about 0.14, so I'll just put 0.14a. And then for 3w, we get 9w squared over 2w squared, which is e to the minus 9/2. And that value is about 0.05, so I'll put 0.05a. And so this gives us enough to plot on our graph here. So I'm going to write in the value for a up on the vertical axis, and I'll write multiples of w on the x-axis. So let's go ahead and plot these points on our graph that I made over here. So 0 we'll put right at a. At 1w we'll put 0.6a, do a little estimation there. At 2w we'll put in 0.14, a little more estimation. And then 3w is 0.05, which is about 1/20th, so get that as best I can. Then I'm just going to mirror those points over to the negative value since this is an even function. And let's connect all the dots there. And you can see that we get a rather bell-shaped curve, and that's the common name for the Gaussian function in mathematics, is a bell-shaped curve. It pops up a lot in statistics. So you can imagine this pulse as, say, if you take a slinky and you just hit it really fast with one jerk up and down, you get a kind of pulse that kind of looks like a bell-shaped curve traveling through the slinky. That's the kind of wave we're dealing with. Now that we know the shape of the curve, let's actually determine what direction it's traveling when we have this x minus vt term as opposed to an x plus vt term. So is it traveling to the right or the left? Well, the way that I would approach this is I would pick a point on the graph that is very unique. And so the most unique point that I can think of on the graph is the peak, the very center top part at x equals 0 and t equals 0. So that peak occurs whenever the exponent is 0. So you get the exponential part of the function is equal to 1, and thus the amplitude is the full amplitude a. So if we track that part in time, we can tell which direction it's traveling. If it's getting larger, if where the peak is getting larger in x, then we know that the peak is traveling to the right, or in the positive x direction. If it's getting more negative, it's traveling in the negative x direction, to the left. So let's explore that. So if we set the exponent equal to 0, that's where our peak is. So we'll set x minus vt quantity squared over 2w squared, with the minus sign out front, it doesn't matter, it'll cancel out anyway, equals 0. Now, this whole quantity is 0 when the numerator is 0, so x peak minus vt has to equal 0. Now we just add vt to both sides, and we see that x peak equals vt. Now we have to figure out what happens as t increases. Well, v is a positive value. We've defined it as the speed of the wave, and speed is always positive. So t is increasing as time goes on. Since that means that x peak equals vt means that as t goes up, x peak becomes more positive, then x peak is traveling in the positive x direction. So indeed, the rules that applied to repeating waves apply in this case to non-repeating waves. So x peak goes up as t goes up, and so we get a total travel in the positive x direction. If we had put x peak plus vt, then we would see that x peak would have equaled negative vt, and then x peak would decrease as t increased. So the rules are the same even with non-repeating waves. So waves don't have to be repeating. This traveling wave is a non-repeating shape, but it is still a traveling wave. It's a disturbance that is propagating through space and time. So the math that we used in this section was mainly about representing functions. We plugged in values to determine different values of x for the function. We used the table of values that we derived from that to make a plot so that we could see the function graphically. And then we changed one and both of the variables to see how the function varies with each of those variables. So we varied it in x to get the plot in x, and then we varied it in time to see how the peak traveled. So go ahead and take a shot at the practice problems, and when you're ready, you can try the do-it-yourself problem.